Good morning, this is your Stat Sensei, Mr. Spensei, and this is the assignment for chi-squared goodness of fit, where this is going to be bloodsuckers. A genetics researcher wants to determine whether the frequency of different blood types in a town with a population of 3,550. Hey, well, that was very nice of them. They even told us we had a population size. It's consistent with the expected frequencies based on the Hardy-Weinberg equilibrium. The researcher randomly samples, okay, 200. So we know we have a random sample. That's good because you know that's going to be one of our conditions. And in this case, they tell us our sample size is 200. And we know we have a population of 3,550. All right. The sample resulted in the following table. We have 85 observed with type A, 31 with B, 8 with AB, and 76 with O. The Hardy-Weinberg equilibrium has the following frequencies. Type A is supposed to be 36%. Type B is supposed to be 12%. AB is supposed to be 3%. And blood type O is 49%. So we listed that there to help us out. All right. At alpha equal 0.05, does a sample uh, at alpha equal 0.05 significance level. Okay, so there's our 0.05. Does the sample determine whether or not the blood are consistent with the frequencies of the Hardy-Weinberg? In other words, are they the same or similar? So we have our observed values. So I went ahead and dropped those into the calculator. And then an L1, and I go stat calc, one var stat. And I find out that I have a summation of 200. And that makes sense because we have a sample size of 200. All right. But this time my expected values, I can't just divide because I have percentages. So I'm going to plug in the percentages they claim. They said 36%. They also said 12%. And they also said 0.03% or 3%. And then they said 49%. So I have those in there, but those are not my expected values. To get my expected values, I'm going to have to go up to the top of L2 and multiply each one by 200. So blue 2 times 200. And what that tells me is I expect 72 because basically what we did is we went 36 times 200 and that gave us 72. 12 times 200 gives us 24. 200 times the 3% gives us 6. And 200 times 49 is 0.8 instead of doing it each one. Because remember, expected value equals NP. Our sample size, which was 200, times each of the percentages. But you can do it real quickly the way I did it. So let me do that one more time so you can see it. So I had 0.36, 0.12, 0.03, and 0.49. Those are the percentages I got from the scenario. I went blue 2 times, okay, and that gave me my expected values. All right, so we have all our expected values and we've listed them in our table right here. Let's look at our formula. Our formula is chi-squared is the observed minus expected. And we know that these values right here are my observed. This is my expected, observed, expected, observed, expected. Notice my expecteds are different this time. All right. And we only care about the first one and the last one. That's not really true, but when we're showing the formula, we're not going to show all four of these. We'll just show um, the first one and the last one. So we can go ahead at this point and we can go ahead and plug in. Oops, that didn't work out quite so well. There we go. All right. So we went ahead and plugged in, and our first observed was 85 minus the expected value of 72 squared divided by 72. And then we're going to skip this one and skip this one and do the last one. And the last observed was 36 minus the expected value of 98. We're going to square it and divide by the expected. Because once again, I'm just going to do this real quickly. This is observed. This is expected. This is observed, and this is expected. Okay? Now, our degrees of freedom. Well, how many levels are there? How many categories? 1, 2, 3, 4 categories. So degrees of freedom are 4 minus 1. Well, we have all that information now, so let's go ahead and run our tests. So stat test, chi-squared, goodness of fit, that's letter D. Our observed was an L1, our expected is an L2, and our degrees of freedom happens to be 4 minus 1. So in this case, we have 3 degrees of freedom. We're going to calculate, and we end up getting a chi-squared value of 9.999 with a 0.0186. All right, so let's look at our graph real quickly, because we can go ahead and graph it. And remember, chi-squared always starts at 0, and it's always positive, and this goes to positive infinity. And we have a chi-squared value of 9.943, and there's our p-value of 0.0186. All right, I also have these contributions, and I'm going to take a moment and report them up here because I'm going to need them later. So there's my contributions. It's not contraband, and I'll have 4 contributions. And we can look at this and go, hey, it looks like the last one, type O, had the largest contribution. Why? Because it's the largest value. And if I added all these values up together, they're going to equal that 9.9943. All right, they will equal that. All right, so we need to say what type of inference procedure. We're running a chi-squared goodness of fit. Our null hypothesis will always start off with each. So in this case, each of the blood types has the same, that's a key word, frequencies as the Hardy-Weinberg equilibrium. The alternative will always start off with at least one of the blood types does not have the keyword, does not have the same, all right, frequencies as the Hardy-Weinberg equilibrium. Right? You're going to see each time we do one of these goodness of fit, each has the same or is the same or are the same or is not the same. Okay? So alternative no will always be the same. The alternative will be not the same. All right, conditions. We have 3. Random sample. And they told us up above in the scenario that we had a random sample of 200, and that was given. So we can go ahead and check that off. When we go 200 times 10 is 2,000. That 3,500 was the population, and that was given to us. So that was good. N is less than 10%. And all expected values are greater than 5. See the table. Let's check our table real quickly. 72, 24, 6. Ooh, 6 is expected. Barely big enough, but as long as it's greater than or equal to 5, all graded. So see the table above, we have our expected values. I'm going to run the test real quickly again. Because the stat test, chi-squared GOF, L1, L2. Degrees of freedom was categories -1, so 4 minus 1. And we ended up with a chi-squared value of 9.943, and that equaled 0.0186. Well, 0.0186 is less than our alpha of 0.05, so our decision is to reject a null. So our p-value is 0.0186, which is less than our alpha 0.05. We reject the null. There's plenty of evidence, so we have sufficient evidence to suggest at least one of the blood types does not have the same frequencies as the Hardy-Weinberg. As always, we're always restating our alternative right here. So let's look back at our alternative hypothesis. At least one of the blood types does not have the same frequencies as the Hardy-Weinberg. So it's super important that you define your hypothesis correctly for this. All righty, I appreciate you watching and look forward to seeing you on the next one. Thank you.